I mean, on the computer we see, on the slate, slate is
on
black.
The tablet. On the tablet also you can see it. There is a version available now.
I see. Got it. Yes.
Okay, I think we can admit participants.
Yes, certainly. Yes, right. I think now we can go ahead with that. It is also on YouTube, so people can see there also.
Right.
Yes, sir. I have already done. Yeah.
Okay.
Sir, whenever you're ready, we can start.
Yeah, anytime.
Yeah, I think it's okay. We can. So let me welcome you all to this session of Math Clinic. I'm very much pleased to introduce an old friend, Professor Katre. He is from University of Pune. Professor Katre received his PhD in algebraic number theory from Punjab University, Chandigarh, in 1985. He joined SP Pune University Mathematics Department in 1988, and till his retirement he was there. From 2012 to 2015, he was also the head of the department in the university. After his retirement, he was invited to join the department again as a chair professor called Lokmanya Tilak chair at SP University, Pune. His areas of interest are varied: algebra, number theory, combinatorics, and of course mathematics education as general also. He has guided 11 MPhil students and more than 15 PhD students. And as I said, he has been helping Maths Olympiad program by guiding students in that program. So today, Professor Katre will be talking about interpolation formulae using Chinese Remainder Theorem. Please, Professor Katre.
Thank you very much, Professor Rana. And I also thank Dr. Soumya Day, who are the organizers of this program under Math Clinic. I thank Professor Rana for giving me an opportunity to give a talk in this Math Clinic, which is a nice activity, as I see, started last year in April. So my today's topic is interpolation formulae using Chinese Remainder Theorem. Usually Chinese Remainder Theorem you see in number theory, also in commutative algebra, and the interpolation formulae are studied in analysis or numerical analysis. So how you will see how these are connected, and there are some standard interpolation formulae which are taught at the BSc and MSc level in mathematics, namely the Lagrange interpolation formula and also Hermit interpolation formula. And we will see how Chinese Remainder Theorem is helpful in generalizing these two interpolation formulae. So in my talk, I will first explain Chinese Remainder Theorem for integers and polynomials, because there is a polynomial version of Chinese Remainder Theorem. Polynomials are close to integers, polynomials over a field. So we will see how you can immediately get this polynomial version from the integer version or an analog of that. Also, this polynomial version can be used to obtain Lagrange interpolation formula. Actually, this is not the way in which the Lagrange interpolation formula is usually proved, but we will see the connection in this talk. And also in the same way, how Hermit interpolation formula can be obtained from Chinese Remainder Theorem. Then we will give application to partial fractions also, because we will have a kind of modified version of Hermit interpolation formula, which is not usually available. At least I have not seen in any textbook. So from that, results about partial fractions can be obtained, which are useful in integration.
Professor Katre,
Yeah.
you can switch off your video because then bandwidth will be saved.
Okay. All right.
Sometimes there's a lag in that.
Yes. Right. Yes. So I will try to do that.
Yeah.
This is not.
Yeah,
Yeah,
sir,
fine.
I have, yeah, okay.
Yeah, it's okay, fine.
You can do that. Yeah, okay. So now these interpolation formulae that we will see, especially in Hermit's one, these are also useful in computer-aided geometric design, or usually it is called in short CAGD. Okay. So first of all, we will see these interpolation formulae. What are these, and then how we obtain these from the Chinese Remainder Theorem. So usually in our high school studies, we study equation of a straight line, and there are different forms of this equation of the straight line. So one is point slope form, another is 2-point form. So point slope form is y minus y naught equal to y1 minus y naught upon x1 minus x naught into x minus x naught, 2-point form. And point slope form is y minus y naught equal to slope into x minus x naught. So these two different ways of getting equation of a straight line, we want to generalize. And we consider the following problems. Find the equation of a curve y equal to fx passing through xi y, and there are n plus 1 points. So I equal to 0 to n plus 1 points, xi y. That is one problem. So from the 2-point form, we want to go to n plus 1 point form, but the equation will not be that of a straight line. It will be a polynomial curve y equal to fx, where fx is a polynomial of degree less than or equal to n. And The second problem is find the equation of a curve y equal to fx passing through xi yi. This is one condition. This one condition involves actually n plus 1 conditions because I equal to 0 to n. And there is one more condition there, derivative f dash xi is equal to yi dash for I equal to 0 to n. So these are again n plus 1 conditions. So we have in all 2n plus 2 conditions here in the second problem. So in the first problem we have n plus 1 conditions. In the second problem we have 2n plus 2 conditions. Okay. So these are the equations that we just mentioned, point slope form. So if you look at this point slope form, y minus y naught equal to slope into x minus x naught. That we can write as y equal to fx, where fx is y naught plus m times x minus x naught. And here this m, that is the slope of the line, is nothing but the derivative of this function fx. Fx is y naught plus m into x minus x naught. If you find the derivative f dash x, that comes out to be m. So here we are giving the value of the function at x naught, and the slope also we are giving. So at x equal to x naught, the value of the function is y naught, and at x equal to x naught, the slope is m. Actually, for any point, because it is a straight line, so it is m only, derivative. So now, first of all, we will look at the problem of finding a curve y equal to fx. Fx is a polynomial in x, and there are n plus 1 conditions fxi equal to yi. And then we try to fit this polynomial curve y equal to a naught plus a1x plus an x raised to n. So there are n plus 1 unknowns here, and there are n plus 1 conditions, and we hope to find out these ai's. So here actually, for the vector space of polynomials of degree less than or equal to n, we are using a basis. That basis is 1x etc. x raised to n, and we are trying to write this polynomial fx in terms of this specific basis, and we are trying to find the coefficients a naught, a1, etc., an. Okay. So how do you do this? We substitute this xi y there. That x equal to xi, then fx is equal to y is expected to be y. That is our requirement. So we get therefore a system of n plus 1 equations. So yi is equal to a naught plus a1 xi plus etc. plus an xi raised to n, where I varies from 0 to n. And then we get the determinant of coefficients. So here the variables are a naught, a1, etc., n, which we want to find out. And the coefficients are 1, x naught, etc., like that. And then we get a determinant of this system of linear equations in n plus 1 unknowns. So this determinant is called as van der Monde determinant. And you will easily see that when you expand this, you get a polynomial of degree n plus 1 choose 2, n into n plus 1 by 2. Because from the first column we are taking 1, then second column we are taking degree 1 term, third column degree 2 term, and so on. In plus 1th column you are taking degree n term, and when you are multiplying these, you get 1 plus 0 plus 1 plus 2, etc., up to n. So sum of first n natural numbers, which is n into n plus 1 by 2. That is the degree of this determinant as a polynomial in these xi, various xi, x naught to xn. And then if I do the operation xi ith row minus jth row, then you will see xi minus xj as a factor there. And then product of xi minus xj will divide it. If you consider these themselves as variables, then easy to see that this is product xi minus xj I bigger than j. So one has to give some argument to see that any constant is there or not, and so on. But this product xi minus xj itself is of degree n plus 1 choose 2, obviously, and one can see that it is like this product xi minus xj I bigger than z. And this is not equal to 0 when xi are distinct. When x0, x1, x2, etc. are distinct, then this is non-zero. That's what we see easily. And then determinant delta I in the Cramer's rule, if you use Cramer's rule, you can get delta I as determinants obtained by replacing the ith column by the column of constants. And so AI have the value delta I upon delta. So this is the usual Cramer's rule method that we use for solving this. And this way you get an expression y equal to fx we get, where we get an expression in powers of x. That means the polynomial fx is obtained as a combination of the basis elements 1x, x square, etc. up to x raised to n. So this is one form of this equation that we get. Here, usually people say that finding determinants is a complicated thing. So it may be taking time also to find out this value of AI. But if you want the answer in terms of powers of x, then this is the way of doing it. But Lagrange thought of a different way. So Lagrange's form. So let us first of all write the equation of a straight line given 2 points on it in the Lagrange's form. So y minus y naught equal to y1 minus y naught upon x1 minus x naught into x minus x naught. This is the standard way in which we write the equation. And then if you rearrange this thing, then you can write in terms of, y0 and y1, a combination of y0 and y1, you can do it. So y equal to y0 into x minus x1 upon x0 minus x1 plus y1 into x minus x0 upon x1 minus x0. This is how you can rearrange and write. Here, the coefficient of y0, usually we don't write in the high school in this way, but this is the way in which Lagrange generalized this result. So equation of a straight line. So here x minus x1 upon x0 minus x1, this is a peculiar polynomial. In this, if you put x equal to x1, then the value is 0. Whereas if you put x equal to x0, then x0 minus x1 upon x0 minus x1. That means the value of the polynomial, this is 1 actually. So similarly, x minus x0 upon x1 minus x0 has parallel property. That means at x equal to x0, this polynomial that you see, actually denominator is a constant, so polynomial is x equal to x0, then it is 0. At x equal to x1, the value is 1. So these are very special polynomials. That is what Lagrange understood. And then to generalize this to n plus 1 points, x0, y0, x1, y1, xn, yn, what we do is we understand this first way is y equal to y0 L0 plus y1 L1. You can write like this. L0 means this polynomial x minus x1 upon x0 minus x1. And L1 is x minus x0 upon x1 minus x0. So this is y equal to y0 L0 plus y1 L1. Now, Lagrange considered this polynomial Lix equal to, as we study in the college level, x minus x0, etc. x minus xi cap, this is omitted term, x minus xn divided by xi minus x0. So replace x by xi minus x0, etc. xi minus xn. So this is how you define the polynomials Lix. And once you do that, the answer is similar to this y0 L0 plus y1 L1. Answer is that one. So these special polynomials, once you use these, the Lagrange's job actually becomes very easy. Lagrange has fx equal to y0 L0 plus y1 L1 plus yn Ln. And at x equal to x naught, the value will be y naught, because at x naught, L naught, x naught is 1, and the remaining things are 0. L1, x naught is 0, L2, x naught is 0, and so on. So y equal to y naught at x equal to x naught. So LIX are called Lagrange polynomials. These are n+1 polynomials, and all these are of degree n. And y equal to fx, it is a polynomial of degree less than equal to n. Remember that when you do combination, the degree can become smaller also sometimes. So, so here, these Li, they also form a basis of the vector space Vn of polynomials of degree less than equal to n. And dimension of this vector space is n+1. So earlier we considered the basis 1x, x square, etc. And now you are considering Lagrange basis L0, L1, Ln. So any polynomial of degree less than equal to n is uniquely written in this form, summation Li, Ai, Lix. That is because this is the basis. And why this is the basis? L0, L1, why do they form a basis? Can also be seen very easily. Because suppose you write 0 equal to b0, L0 plus bn, Ln. If you put x equal to x0, then L0, x0 is 1 and others are 0. So that means 0 equal to b0 into 1. So b0 equal to 0. Similarly, if you put x equal to xi, then bi becomes 0. So this is a basis, and polynomials, any polynomial of degree less than or equal to n is uniquely a combination of L0, etc. up to Ln. So now we see Hermit interpolation, and then we will see the connection with the Chinese Remainder Theorem. Interestingly, Hermit was born in 1822. So this year is 200th year of his birth. That is 2022. Now, Hermit considered the other way of writing the equation of a line, y equal to y naught plus m into x minus x naught, or y equal to y naught plus derivative, m is derivative, f dash x naught is equal to m, y equal to fx is what we are interested in. So now you can ask the analogous question, as I mentioned earlier, find a polynomial fx such that f of xi equal to yi, 0 less than equal to I less than equal to n, and f dash xi is equal to yi dash. And then this curve y equal to fx we want to try to find out. So how many conditions are there? N plus 1 plus n plus 1, that is 2n plus 2 conditions are there. So you should go up to degree x raised to 2n plus 1 in this case. If you want to, so because 2n plus 2 conditions are there, so 2n plus 2 variables, n0 to a 2n plus 1. Now you can have yi equal to a0 plus a1 xi plus etc. plus a to n plus 1 into xi raised to 2n plus 1. And then yi dash, you can find derivative, and yi dash equal to a1 into 1 plus 2a2 xi plus 2n plus 1 a to n plus 1 into xi raised to 2n. So these are the new n plus 1 conditions, which were not there earlier in the form of Lagrange. These are new conditions. So we get linear equations, 2n plus 2 linear equations, and we get a determinant as before. Now, if the determinant is non-zero, then we can certainly have ai equal to delta I upon delta. So you may try to see whether, can you show that this determinant is non-zero? But I assure you that it is non-zero actually. Whenever the x0, x1, xn, they are distinct, then this is non-zero. You see that if you look at the first n plus 1 rows, then xi minus xj is a factor there, okay? And the next n plus 1 rows coming from derivative, if you look at them, so n plus second row and the last row like that. So these are n plus 1 rows, and they are also you can consider ith row minus jth row, and again xi minus xj kind of thing will be a factor there. So certainly this determinant is divisible by a product xi minus xj square. And what is the remaining thing we don't know, means we have to really solve it and find out. But so I can assure you that this determinant, actually one can simplify, and the answer is plus or minus van der Waals determinant raised to 4. That is square we have already obtained by this observation. But when you simplify completely and try to factorize this, if you are able to factorize, you will get van der Waals determinant raised to 4. That means van der Waals was earlier xi minus xj, product of xi minus xj. That was van der Waals determinant. Probably yes. This was van der Waals determinant, product xi minus xj, I bigger than j. This was non-zero. And this new determinant, when you get the derivatives also there, and 2n plus 2 conditions are there, at that time, this new determinant is fourth power of this, essentially. Fourth power. So product xi minus xj bracket raised to 4. And sign may be there plus or minus. That is immaterial for our problem. So in any case, it is non-zero whenever these are distinct. X0, x1, etc. Whenever they are distinct, then this determinant is non-zero. And our Kramer's rule works. AI is equal to delta I upon delta. This formula is there, and we are able to write the solution curve y equal to fx in powers of x by this method. But then Hermit doesn't do it this way. He follows Lagrange's method. And just as Lagrange considered combination of this yi with something, so he does tries to write the answer y equal to fx as combination of yi and yi dash. That is what Hermit does. So the question is that find out this curve y equal to fx such that f of xi equal to yi and f dash xi is equal to yi dash. That means not only that the curve is passing through xi yi, but also at xi yi there should be the given direction, that is yi dash or f dash xi. That is the given direction. So because the direction is also given, probably you can get the shape that you want for the required curve. That's why this is very important in computer-aided geometric design. And the answer of Hermit, as you will see, is this h2n plus 1. Here is h2n plus 1 because this is a polynomial of degree less than equal to 2n plus 1. And it is written as a combination of yi and yi dash. So summation yi h n comma I x plus summation yi dash h n comma I cap x. So hni and h hat ni. These are two polynomials, and they are obtained by a specific formula. They have some specific properties. If you look at Lagrange thing, Lagrange polynomial, suppose Li, it has the property that Lixi equal to 1 and Lixj are 0. That is how these properties are useful, I mean, for the Li. So here also Hermit considers similar things. So what are the requirements of Hermit here? Hni x at x equal to xi is 1 and 0 elsewhere. That is for the values of the polynomial hni x. And derivatives. The derivatives are 0 at all xj, including I. That is the requirement for hni. Now h hat ni, what are the requirements? Derivative at xi is 1 and derivative is 0 at all other xj. Whereas the values are 0 at all xj. This polynomial h hat is 0 at all x0, x1, x2 up to xj. So hni, it has the property that all derivatives are 0. H hat has the property that all the values are 0 at the xj. And for HNI, value at xi is 1. At other points, value is 0. For h hat, what happens? Derivative at xi is 1 and the derivative is 0 elsewhere. So this is kind of imitating Lagrange. Hermit was able to find out these polynomials HNI, and these can be obtained by some trial. So Hermit's idea is to follow Lagrange's method and construct polynomials like Lagrange's to satisfy the requirements. Lix, Lagrange was Lix equal to 1 at xi, 0 at xj. Hermit, HNI, 1 at xi, 0 at xj for j not equal to I, and derivative are 0 at all xj. H hat, value is 0 at all xj, derivative 1 at xi and 0 at xj, j not equal to I. Such HNIX and H hat NIX, they are obtained as follows. So this is Hermit's formula. HNIX is equal to 1 minus 2 times x minus xi L dash Ni xi. L dash, L is Lagrange polynomial. L is that product x minus xj except for I, and denominator product xi minus xj. So that is Lagrange polynomial. Take its derivative. That is here in HNI and multiplied by L square x, Lagrange square. Now H hat is x minus xi times L square Nix. So now you will see that it actually satisfy our requirements. For example, H hat, you require that it should be 0 at all xi. So is it 0 at x equal to xi? Yes, because of this factor, x minus xi. Is it 0 at other xj? Yes, because of the second factor. Because Lagrange polynomial is 0 at x equal to xj whenever j is not equal to I. Okay, Lni or Li is 0 whenever x is equal to xj, where j is not equal to I. And derivatives, you can actually calculate the derivatives. So for example, at x equal to xi, what is the derivative? So you know derivative of product of two functions. So derivative of x minus xi is 1, and derivative into this polynomial at x equal to xi. But L square at xi is equal to 1, you see. Similarly, first term x minus xi into derivative of second thing. But you see, because of the first term it is 1, and whatever that derivative is at x equal to xi, the value is 0. So the answer is derivative is 1 at x equal to xi. And you can also see that derivative is 0 at other points. And HNIX, if you see, this has derivative at xi equal to 0, can be seen. It is just a manipulation, you can check that. And therefore, we get a formula now. The formula is, or Hermit's formula is, that it is a combination of yi and yi dash, like Lagrange. Yi times the Hermit polynomial HNIX plus here summation yi dash times H hat NIX. So this is the Hermit's interpolation formula. And this follow essentially the Lagrange's idea. Here you see that the answer is in terms of the derivative of the polynomial L. L is Lagrange polynomial. And you see that in the formula for HNI, the derivative is involved, and we have to calculate this derivative, which is not actually done here. But if you do that, then you will get a simpler formula. So this calculation you can try to do, and then you will see that you can get a simpler formula than Hermit's, which is fx equal to summation I equal to 0 to n yi plus beta I times x minus xi into li square x. So this Li square was there actually, and the other things can be combined in this way. And beta I is in terms of yi and yi dash. So beta I is yi dash minus 2 times yi summation 1 upon xi minus xj, j not equal to I. J not equal to I. So this is the formula which does not involve any derivative, and once you know yi and yi dash, you can write down this thing. And if you like, you can write it as a combination of, so yi times something plus yi dash times something. That way also you can write it if you like. That is what Hermit had done. So now we want to see general interpolation formula and how Chinese remainder theorem is useful there. And we'll also try to see how these two formulas also can be derived from Chinese remainder theorem. So what is general interpolation formula? General interpolation formula means you have the points x0, x1, x2 up to xn. At all these points, you are given the value of the function, a polynomial function. Now at some points you are given derivative. At some point you are given derivative and second derivative also. At some points you are given derivative, second derivative, third derivative, like that. Only thing is, it is you should not do like this, that you give the value of the function, then omit the derivative and directly give second derivative. You should not do something like that. You should continuously give these things. So fxi, f dash xi, f double dash xi up to f say nu minus 1 xi. So you give continuously the value and the derivatives up to some stage, whatever you like. So the derivatives known can be different at different points. Now such a polynomial is uniquely determined as a polynomial of degree less than equal to nu0 plus nu1 plus nu(n) minus 1. And this is a consequence of the polynomial version of Chinese remainder theorem. Moreover, the unique interpolating polynomial can be algorithmically obtained. That's what we want to see. So what is Chinese remainder theorem for integers? So the question is, in usual remainder language, you are given some moduli, m1, m2, mr, and you want a positive integer, say, which when you divide by m1 leaves remainder a1, divide by m2 leaves remainder a2, divide by mr leaves remainder ar. Can you find such a positive integer? Now, in the modular notation, you ask the same question like this. Can you find integers x satisfying x congruent to a1 mod m1, x congruent to a2 mod m2, x congruent to ar mod mr? Now here you can even take negative integers. So remainder is 0 or positive. That requirement is not there now. We can even say x congruent to minus 7 modulo 100 or something. That is also allowed. So that is the usefulness of modular notation. And then the Chinese remainder theorem says that the answer is there whenever m1, m2, mr are relatively prime in pairs. So m1 is coprime to m2, m2 is coprime to m3, m1 is coprime to m3, and so on. In any, so any two mi and mj are relatively prime. Then there is a unique solution modulo m1, m2, mr. Moreover, you have a formula for the answer. X is congruent to a1, capital M1 dash, plus etc., plus ar, capital mr, capital mr bar or dash, whatever you like. What is this? What are these capital mi? Capital mi means take the product small m of m1, m2, mr and divide by small mi. So capital Mi is m upon small mi. That means it is the product of all other numbers, product mj, j not equal to I. So that is capital Mi. And this m1 bar, m2 bar, mr bar, they are defined like this. Mi bar is any integer satisfying mi bar is congruent to 1 mod mi. So this mi bar is an inverse of capital Mi modulo small mi. because their product is 1 modulo small mi. So this is an inverse. So this mi bar you can choose to be a number between 1 and mi minus 1. So it is less than mi and bigger than or equal to 1. It cannot be 0 because mi bar is congruent to 1 modulo small mi. So it is between 1 and mi minus 1. Such a number you can choose. And it is unique modulo small mi, means you can add mi, 2 mi in this, 2 times small mi, etc. in this. That is also an inverse because the modulus is mi. So if you add or subtract these multiples of mi, there is no problem. So let us just see an example for revision. Suppose you want to solve x congruent to 1 mod 3, 3 mod 5, 2 mod 7. Then these are numbers relatively prime in pairs and product of them is 105. So we make a table for convenience that mi is equal to 3, 5, 7. Capital Mi is product of other numbers. So 3 means 5 into 7 is 35. So here 21 means 7 into 3, other two numbers. 15, 3 into 5 is 15, like that. Now you want to find capital Mi, its inverse, modulo small mi. So let us reduce capital Mi modulo small mi. So small mi is 3 and modulo 3, 35 is nothing but 2. Because if you divide 35 by 3, then the remainder is 2. Similarly, 21. Modulo 5, it is 1. 15. Modulo 7, it is 1. Because 15 minus 14, that is a multiple of 2, 7. So it is 1. Mi bar means the inverse. So you have to find the inverse of 2 modulo 3. But 2 into 2 is 4. 4 means 1 mod 3. So 2 is the inverse of 2. It so happens that 1 is the inverse of 1 and 1 is the inverse of 1. Same numbers are appearing here as inverses. No problem for us. Now AI are 1, 3 and 2 in our problem. 1, 3 and 2, they are the AIs. So our formula is A1, M1, M1 dash, etc. A1, M1, M1 bar, A2, M2, M2 bar, AR, MR, MR bar. So let us do that. So here A1, M1 35 and M1 bar. So that is 2. So product is 70. Similarly, 21 into 1 into 3 is 63. And similarly here we get 30. And the sum of all these things is 163. That is the answer. X is congruent to 163 modulo 105. If you want, you can write it as 58 also, because 58 is congruent to 163 modulo 105. And this is a smaller number. We prefer that. So the answer is 58 mod 105. And this is the least positive solution for the problem. All solutions, if you want, X is 58 plus 105 K is in Z. So this Mi bar can be obtained by trial, or if the numbers are large, suppose M1 is 1,75,500, etc. Then you have to do Euclid's algorithm or Kuttaka method. In Indian mathematics, we have Kuttaka method. Old method given by Aryabhatta is there. You can use that also and get the inverse. Now, polynomial version of this Chinese Remainder Theorem is, instead of numbers, we take polynomials. So polynomials over a field, real numbers, complex numbers, finite field, any field you can take. And over that field, you take polynomials and you ask the same question. Suppose MIX are polynomials. MIX are relatively prime in pairs. They don't have any GCD. GCD is 1. Then consider fx congruent to fix mod MIX, system of congruences. These are polynomial congruences. And the theorem says if MI are relatively prime in pairs, then this system of R congruences, I equal to 1 to R, let us say, it has a unique solution modulo MX equal to the product M1x, M2x, MRX. So if the degree of mx is d, then you will get a unique solution as a polynomial of degree less than or equal to d minus 1. And the answer is given by the same formula, which is there for numbers. Summation fi mi bar, where capital Mi means mx upon mix. Same thing, same formula. Mi bar is such that mi bar is equal to congruent to 1 mod mix. That means a difference between this left hand side polynomial and 1, that difference is divisible by mix. That is our requirement. Such a mi bar x is called inverse. And mi bar can also be obtained using Euclid's division algorithm for polynomials. GCD algorithm actually, not, the next algorithm is division algorithm. Instead of that, you use GCD algorithm. And Indian Kuttaka method also you can use. Whatever is for numbers, same thing you do for polynomials. That is the Indian Kuttaka method. That will also give you the value of mi bar x. So for big polynomials, a computer can do this job if you want. So mi bar is unique modulo mix. It is the least degree polynomial mi bar x satisfying mi bar equal to 1 mod mix has degree less than degree of mix. Of course, yeah, it cannot be 0, so it has some degree and it is like this. Okay. All solutions if you want. If Gix is one such polynomial, then you can add multiples of mix. So Gix plus hi into mi also works as inverse of mix modulo. Okay. So now just this simple example. X square minus 1 into x square plus 1 is x raised to 4 minus 1, we know. So if you go modulo x raised to 4, what happens? Modulo x raised to 4, this product is minus 1. So we write 1 as, change the sign here, 1 minus x square into x square plus 1. Okay. 1 is equal to 1 minus x square into x square plus 1 modulo x raised to 4. We are forgetting x raised to 4. So it is modulo x raised to 4. And then these are polynomials whose product is 1. So they are inverses of each other. Suppose this is mi, then this is mi bar. Okay. So like that. So this is just an example. Another example is, suppose fx is a given polynomial, and we know that fx is congruent to f7 modulo x minus 7. Okay, that remainder is f7. If you divide fx by x minus 7, then the remainder is f7. That we know, remainder theorem. So fx congruent to f7 modulo x minus 7. So if f7 is not equal to 0, you can divide by that. And we get fx into 1 upon f7 is 1 mod x minus 7. And this is a constant polynomial. 1 upon f7 is a constant polynomial, which will work as inverse of fx modulo x minus 7. Okay. So if the polynomial is linear, it is very easy to find the inverse. Like this. Fx has inverse 1 upon f of, say, a. If you are going modulo x minus a. All right. So that's easy. Now, general interversion formula we want to get. So what we do here, as I said, fx is a polynomial which is required to have values fxi, f dash xi, etc. up to f mui xi, let us say. As these values are yi dash, and mui's derivative is yi raised to mui. And this happens for I equal to 0, I equal to 1, I equal to n. So these mui are they can be different or they can be same. That is up to you. So what we do, we define aix equal to yi plus yi dash x minus xi plus yi second derivative, means it is the notation yi2 upon 2 factorial. This is the value. yi2 is the value of second derivative at xi. So like that, up to yi mui factorial upon mui factorial x minus xi raised to mui. So now we are using Taylor's theorem here. Using Taylor's theorem, if you want to expand any polynomial, then the initial terms in powers of x minus xi are like this, that the value of the function at xi, then derivative into x minus xi, second derivative upon 2 factorial x minus xi square, and so on. This is the Taylor expansion. And you can stop anywhere. What remains is powers of x minus xi, mu I plus 1 onwards. Okay, mu I plus 1 onwards. Therefore, I can say that fx is congruent to aix modulo x minus xi raised to mu I plus 1, because other terms are divisible by this x minus xi raised to mu I plus 1. And here Taylor's theorem is useful for polynomials. Okay, so fx satisfies. So all these, see, interesting thing is all these conditions, mu I plus 1 conditions are there. We are writing in terms of a single condition using the congruence notation. We are saying that all these mu I plus 1 conditions are equivalent to the single condition fx congruent to aix mod x minus xi raised to mu I plus 1. So this is an interesting part of it, that you are writing in the congruence notation. And now, once it is in the congruence notation, and we know that when x1, x2, x0, x1 are distinct, the polynomials x minus xi raised to mu I plus 1, they are mutually co-prime. Therefore, we can use Chinese Remainder Theorem for polynomials, and you can get this answer: fx equal to summation aix, mix, mi bar x mod small mx, means small mx is the product x minus xi raised to mu I plus 1, I equal to 0 to n. This is the answer. Even if the derivatives are different for different points, that means for the first point we can take derivative up to first derivative, second derivative, for the second point you can take derivatives up to fourth order, and so on. Even then you can get this answer. The only trick is that to find out mi bar x, how to find out mi bar x. But mi bar x is the inverse of mix modulo x minus xi raised to mu I plus 1. Mix is, as we know, mx upon x minus xi raised to mu I plus 1. So you can find out the inverse using Euclid's GCD algorithm or Indian Kuttaka method. Actually, Indian Kuttaka method is written for integers, but the same thing you can use for polynomials too in the similar way. Okay. So now the polynomial of smallest degree satisfying the given conditions, it has the degree summation mu I plus 1. Mu I plus 1, you know, is the degree of this x minus xi raised to mu I plus 1. That mu I plus 1 is here. Summation of that minus 1. That is, you can, this is 1 plus 1 n plus 1 times minus 1. So it is n here. Summation mu I plus n. That is the smallest degree of polynomial of smallest degree which satisfies the given conditions. And the solution exists and is unique with this condition. Okay, now let us see how Lagrange this interpolation formula we get as a consequence of this general interpolation formula. So here all the mu I are 0, right? Because you are only having fx equal to y. We are not having derivative involved here. Okay, only fx equal to y in the Lagrange's case. So we can write the congruence condition as fx congruent to y mod x minus xi. This is remainder theorem basically. That fx is congruent to y mod x minus xi. This is the important step. Now what is capital Mix? Product x minus xj, j not equal to I. What is mi bar? See, you are going modulo x minus xi. So the inverse is just 1 upon mi xi, as we have seen in the example. Just substitute x, replace x by xi, and then take 1 upon that. 1 upon mi xi is the inverse of mix. So mi bar x. Mi bar is nothing but 1 upon mi xi. So our formula, Chinese Remainder formula, what does it give you? Fx equal to summation yi mix into mi bar x, but mi bar x means 1 upon mi xi modulo mx. And now What is mix by mixi? That is our Lagrange polynomial Lix. Lix is mix upon mixi. That is, it is the polynomial product x minus xj not equal to I. That is, numerator is mix. And denominator is product xi minus xj not equal to I. So it is, this is the Lagrange interpolation formula that we get from general remainder formula. The interpolation formula. So partial fractions now, how do you get from this? Because I wanted to connect to partial fractions also. So we have this Lagrange interpolation formula, fx equal to summation fxi mix upon mixi. Now you divide by product x minus xi, I equal to 0 to n. What do you get? Fx upon this thing, product. So denominator is a product of linear polynomials, n plus 1 linear polynomials. Now you want to write into partial fractions. But on the right hand side, mix is the product of all x minus xj except I. So 1 upon x minus xi, that is remaining there. And in the numerator, fxi divided by mixi. This is the constant there. Fxi upon mixi upon x minus xi. So this is the partial fractions formula we get from the Lagrange's interpolation formula. And we want to see what happens if denominator is x minus xi square. Okay. Let us see that also, that we get from the version of Hermit that we have obtained, I mentioned. So now how to get Hermit formula from general interpolation formula. So here mx is product x minus xi square, right? Capital Mix means product x minus xj square, j not equal to I. Our modulus is x minus xi square, okay? And our congruence condition is fx is congruent to yi plus yi dash x minus yi dash into x minus xi. This is a kind of Taylor's formula I mentioned, but here only first derivative is there, so it is very simple. And now the solution we know in terms of mi bar. So we should find out mi bar. So what is mi bar? Mi bar is the inverse of mi. So mi into mi bar is 1 mod x minus xi square. So you can take mi bar equal to constant plus constant times x minus xi. Okay, because you are going modulo second degree polynomial. So answer is up to first degree. So you have to find out ai and bi. But now in this mi bar equal to 1, you just put x equal to xi. Then you get mi bar xi is 1 upon mixi. And in this also you put mi bar equal to, so put x equal to xi in this. So mi bar xi is ai only, because this part becomes 0 when x equal to xi. This modulus also that is 0. So ai is equal to mi bar xi. And what is bi? Bi, actually it is a derivative. If you differentiate fx with respect to x and put x equal to xi there, then constant derivative is 0. This is yi dash derivative, and derivative of x minus xi square is actually 0 at xi. So we don't have to bother about that term. Even if any coefficient is there, we don't have to bother about that term, that we can see easily. So bi is mi bar dash xi, and that you can find out. What you just do is, I don't spend much time on that. You just take mi bar equal to 1 mod x minus xi square, differentiate both sides, and then on left hand side, product of two polynomials is there. So first into second, derivative of second, plus derivative of first into second polynomial, etc. Derivative of one is 0, and at xi the derivative of this is 0. So differentiate and put x equal to xi, you get 0. So you get this mi dash xi into mi bar xi plus mi xi, etc. is 0. Therefore, bi is equal to mi bar dash xi is this formula. You can just put it here, and mi dash xi comes out to be 2 times mi xi upon xi minus xj. Now these are simplifications which we have to do, and then you have to check this thing that it can be simplified. to this formula, and bi comes out to be this. Once you do this, you get fx is equal to this formula that I mentioned, comes out here. So this is ai, our formula, summation capital AI mi bar. So mi bar is this thing, mi is here, and this is ai, and if you simplify this, you will exactly get yi plus beta I x minus xi into mix upon mixi, where beta I is what I have mentioned. Beta I is yi dash minus 2yi summation 1 upon xi minus xj. So this is the final formula, which is simplified formula as compared to the original Hermit formula. And Li, capital Li, this is script Li I have written, which is Lagrange polynomial square of the Lagrange polynomial. Okay. Capital Li is product x minus xj square upon product xi minus xj square. So this is the simplified Hermit interversion formula, and which I have obtained. So now we have generalized interversion formula with us, and so you can go to higher derivatives also if you like, and different derivatives also at different points. So all that is fine. Now the last thing is partial fractions in this case. So we have now fx equal to this with us. Divide this by product x minus xj square for all I, all j means. So you get this fx upon product j equal to 0 to n x minus xj square is equal to, now you are dividing by this. So capital mix is there in the numerator. See, lix is there means capital mi. Capital mi means all other terms then j equal to I. Okay, we require j not equal to I here. So when you divide all this product by product xi minus xj square for all j, then what remains is x minus xi square in the denominator. Okay, so it is like, you know, dividing this thing by x minus xi square. So you get yi upon x minus xi square and beta I upon x minus xi square. But this thing is there that we have to consider. So you get final formula for partial fractions is fx upon product x minus xj square is equal to summation beta I upon script mi xi, that is the square actually, and upon x minus xi plus yi upon script mi xi upon x minus xi square, where capital script mi xi is product xi minus xj square, they not equal to I. So this is the partial fractions formula, and I think you will be confident in integrating such a thing. Fx is a polynomial of degree less than or equal to 2n plus 1. If it is divided by this thing, then you can integrate this very easily by using this formula. So this is an application of this new version that I have obtained from the using the Chinese Remainder Theorem. Yes, so there is one reference which I would like to give to you. That is, there is an article which I have written in Bulletin of Mathematics Consortium, Volume 3, October 2021. Title is Chinese Remainder Theorem and Interpolation Formulae. And it is available at the website themathconsortium.in, where all the issues of Bulletin of Mathematics Consortium are there, and various articles. I think one article of Rana sir is also there. You can see various articles on different interesting topics. You can see that. So thank you for your patience. I'm through. Yes. So I think I should stop sharing. Okay. All right. In case if people have questions, that's fine. But basically, I have shown how these things are connected. That means Chinese Remainder Theorem, Taylor's theorem, interpolation formulae, etc. And integers and polynomials. Chinese Remainder Theorem for integers and polynomials, how it is useful in the interpolation formulae. Yeah. Oh, sir.
Hello.
Sarana, sir, we cannot hear you. You are muted, I think. People are muted, so I think they have to be unmuted by the organizers.
Hello.
Yes, we can hear you.
Yes, it was very interesting. Thank you.
Thank you. Nice.
I taught numerical and I'm teaching numerical analysis currently. So all these Lagrange polynomials, Hermit polynomials, they are being done.
Yeah.
So this is a very nice way to look at those things.
Yeah. Yes.
Good to see you too after a long time.
Yes, yes. We can see you also if you show yourself. Anyway.
Yeah. Now I think maybe I should wear my glasses.
Yes, right. Yeah, because the usually one can go to third derivatives and so on, but these formulae are not mentioned usually because they become more and more complicated. To guess the, in the Lagrange's way, you have to guess the polynomial Li, which is easy actually. And then in the Hermit's method, which follows Lagrange's method, you have to guess this H and H hat. Now, if you want to go for second derivatives, then we have to guess, let us say, whosoever, suppose Sipart does it, then S hat, H double hat, and so on. More and more polynomials you have to guess. So like that. But this generalized method tells you everything. Only thing is you have to find the inverse of this MI or whatever polynomials are there. You have to find the inverses. So that's.
There is actually
how they do it. Yeah.
Yeah, there is a method called divided differences by Newton.
Yes.
So I wonder if there is an analog of divided differences in number theory, which can be used to derive these, the Chinese Remainder Theorem and so on. I wonder if that is possible.
One can see that. Yes. Good
Yes.
idea. So, that way you can see whether there is a simpler way of looking at these things.
Yeah.
And so on.
So all these higher derivatives and so on, all those values can be computed using divided differences.
Yes, right.
That is one way. So if that is there in, of course, meaning it is difficult because it uses derivative. So worth thinking, trying to see whether there is an analog.
But here I'm saying that you can take different derivatives also.
Yes, higher derivatives and so on.
That is, for one point you take only second derivative. For second point you take up to fourth derivative you can go and so on. So you can answer this more complicated looking question also.
Yeah.
Okay, I think if there are no other.
If I may ask one question.
Yeah, please. Yes, right.
The polynomial that you get, suppose you start from a ring, the polynomial that you get, the coefficients are in the fraction field or they are in the ring only because you were dividing at many
Yes, yes. Certainly you have to go to the quotient field.
Quotient
So this works for any field. This formula, interpolation formula works for any field. And if you only take integral domain, then you have to go to quotient field because we are dividing. So basically this interpolation formula, all these interpolation formulae work for any field actually. It can be real, complex or finite field also, but the same thing works.
Not necessarily ring, means we will leave the ring.
Ring means, of course, integral domain you can take, and divide means you have to go to quotient field.
Okay, thank you.
Yes, thank you.
Any other questions? Comments? If not, I would like to once again thank Professor Katre for coming over and illuminating us. Don't think of there is something called pure and there is something called applied. What is somewhere
Yes.
for the other, right?
Yeah, very pure thing can be used for applied things.
Yes, surely.
Yes.
Thank you very much, and thank you everybody for joining. Please take care.
Thank you. Yes.
जैसे हाथी निकल गया है, पूंछ अभी बाकी है.
Yes, that's right.
Do take care. Yes.
Thank you.
Thank you.
All right. Thank you.
Bye.
Bye.